So in some previous lessons, I had alluded to this power rule, how the base and the argument can be powered up together. Okay, so if I have base A, I can power that A by some factor of m, and power the argument by the same factor, and those powers balance each other off, and they're equivalent to what we started with. Okay, and the ratio of these powers can be simplified. Okay. And well, I'm just going to justify why this is true. So we can justify it in a few ways. One way is this. We can just say that, okay, well, if I have a power 2 and a power 6, they have share a common factor of 2. And I can divide out this 2. I can actually reduce this ratio by a factor of 2. I can make this 1 and 3. Well, how can I justify that? Well, if I rewrite it in its exponential form, it looks like this. A squared to the power x, which is 2x, equals the logorand, or the argument, which is 6y. And this ratio of powers can be simplified because I can square root both sides, and this ratio of 6 to 2 reduces to 1 to 3. And I can rewrite it in this form. Yeah, that power, same power x, exactly same power. We didn't change the value of the power, but we reduced the ratio of these powers by a factor of 2. So I can power the argument and the base the same. And just make sure you understand the reasoning. It's because notice where the base and the argument show up on the equation, on the balance. What I do to one side, I can do to the other. So if I scale this by a factor of 2, I can scale this down by a factor of 2 as well. I can justify this also with a change of base. Okay, so if I change this to change the base formula and bring those powers out, notice that that ratio of powers again exists. There's that power 6, power 2. I can square root, okay, and that ratio of powers reduces to 1 to 3. Okay, so again, there's an equivalent. These are equivalent. This is the same as this. The x didn't change. Okay, so this expression here is equivalent to this expression here. This ratio of 2 to 6 is equivalent to 1 to 3. And we can justify this by, we can see that, yeah, if we use power rule here, we can justify the ratio of those powers being reduced. We can also do this by definition of the definition of exponent of base A. So if I look at this as a base A exponent, okay, I can then say that this base, I can power this base exponent can go onto the log, because that exponent log, the x there, is the exponent on this base. Well, I can just transfer that exponent to the exponent side of the equation, and that should be true. Okay, and if we want, we can then, apply our power rule, and we can see again that algebraically we can simplify that as a ratio of 6 to 2, 3 to 1. Okay, and we can show again that this expression here is equivalent to the original expression up here. Okay, so we can justify this because this is the exponent on this base. Well, that exponent should show up as part of as what the log is equal to. So those are equivalent. Okay, those are the equivalent position in our algebraic expression. So this is a very much deeper way of understanding logs. And if you understand how this all works, you're starting to develop a very deep understanding of logs and exponents and how they interact with each other. And this is a very difficult thing to do, but if you can get there, you'll have a much deeper and richer understanding of how logs and exponents actually work.